Hello and thank you for watching my video. My name is Astrid Krasniqi. This is chapter 8 IP addressing. This is part 2 or 8.2 IPv6 network addresses. Now we'll continue with this with IPv6 now. We covered IPv6 part 1. The need for IPv6. IPv6 is designed to be the successor of IPv4. So depletion of IPv4 address space has been the motivation factor for moving to IPv6. Projection shows that all 5 RIRs will run out of IPv4 addresses between 2015 and 2020. I just saw an article on the web that they said that IANA has actually run out IPv4 addresses to be assigned to RIRs. RIRs, I still have some IPv4 addresses. With an increasing internet population, a limited IPv4 address space, issues with NAT and the Internet of Things, the time has come to begin the transition to IPv6. IPv4 has a theoretical maximum of 4.3 billion addresses, plus private addresses in combination with NAT. IPv6 has the largest 1 to 8-bit address space, provides for 340 undecillion addresses. IPv6 fixes the limitation of IPv4 and includes additional enhancements such as ICMP v6. Look at this. This is the IPv6 header. So when you look at it, it's got quite large source and address space because it is using 128 bits instead of 32 bits of IPv4. IPv4 and IPv6 coexistence. There is not a single date to move to IPv6. For the foreseeable future, both IPv4 and IPv6 will coexist, and transition is expected to take years. It's already taking quite a few years. We have some transition methods that we have. For example, the first one is dual stack. It's very popular. Dual stack allows IPv4 and IPv6 to exist on the same network. Dual stack devices run both IPv4 and IPv6 protocol stacks simultaneously. Then we have a tunneling. Tunneling is a method of transporting an IPv6 packet over an IPv4 network. The IPv6 packet is encapsulated inside an IPv4 packet, similar to other type of data. So we have IPv6 here, token, and then we encapsulate IPv6 inside IPv4. Translation, network address translation 64, NAT 64 allows IPv6 enabled devices to communicate with IPv4 enabled devices using a translation technique similar to NAT or for IPv4. An IPv6 packet is translated to an IPv4 packet and vice versa. So here we have one side is doing IPv4, the other side has got IPv6, and the NAT64 is going to do translation between these two different protocols. Hexadecimal numbering system. Unlike IPv4 addresses that are expressed in dotted decimal notation, IPv6 addresses are represented using hexadecimal values. So as MAC addresses or Ethernet Media Access Control addresses are represented in hexadecimal values. Hexadecimal numbering. Hexadecimal, or hex for short, is a convenient way to represent binary values. Just as decimal is in base of 10 numbering system and binary is in base of 2, hexadecimal is in base of 16 system. The base 16 numbering system uses the number 0 to 9 and then the letters A to F. For example, they start the hexadecimal base 16, so we can have 0 to 9, same as decimal. Then for 10 we have A, B for 11, C 12, D is for 13, E is for 14, and F is 15. That's the maximum. F is the maximum. So what happens with 16? Now when it's 16, it's 1, 0, and then it starts 1, 1, 1, 2, up to 1F again, and then it starts again 2, 0, and so on. It will continue. IPv6 address representation. So IPv6 addresses are 128 bits in length and written as a string of hexadecimal values. Every 4 bit is represented by a single hexadecimal digit, for a total of 32 hexadecimal values. IPv6 addresses are not case sensitive, and we can write them in either uppercase or lowercase. So we have every digit, this is hex digit, it will represent 4 bits, for a total of 32 hexadecimal values. So for example, this is a IPv6 address, 2 IPv6 addresses, one global, one linked local. So this number 2 here is not actually a 2, it's in binary, it's representing a binary, 4 bits in the binary. So this 2 is actually 0010, and this 0, there's 4 zeros, And then this 0 is representing 4 bits of zeros, and this 1 is representing 1 in binary, so 0 0 0 1. So let me bring that notepad here. Let's make some space. So for example, IP address 2001, right? This is represented in hexadecimal. So when we look hexadecimal, 2 is actually like writing it 0 0 1 0 0 0 0 0 0 0 0 0 0 0 0 1. Press F1 there by mistake. Okay, so this 2 here is representing 4 bits. This 0 is not representing another 4 bits. This is representing another 4 bits, and this is representing another 4 bits. So in total, there is a 16 bits for each hexstat. These are called hexstat as well. 16, 32, and 16 is 48, and 16 is 64, and then we'll continue up to 128. So like I said earlier, the one value or hexstat is known, is representing actually in binary is representing 16 bits. So IPv6, for example, first thing we can do is omit leading zeros. The first rule to help reduce the notation of IPv6 addresses is any leading zeros in any 16-bit section of hexstat can be omitted. So for example, if this is our IP address 2001 0db8, like preferred right in our IPv6 address, 09F0 0A00, all zeros, and then 001. What we can do is we can remove the leading zeros. So here there's no leading zeros, but here there's start with 0, so that's a leading 0. We can remove that. We can represent that as just db8. Here we have another leading 0. We can remove that, but here we have a trailing 0. We can't remove that, so it has to be 9F0. Again on 0A00, again we have one leading 0. We can remove it, but 2 trailing zeros we can't remove them. Here we have 3 leading zeros. We can represent it just by 0. And then again, same thing. And the third, this hexet as well, the same thing. Then we have another 3 leading zeros. We can remove them. We can say by 1. So in the compressed version, we can say this IPv6 address, we can say 2001 colon db8 colon 9f0 colon a00 colon 0 colon 0 colon 0 colon 1. Now it has to be a colon, no semicolon, no comma, no dash. It has to be with a colon. Omitting all 0 segments. So for example, a double colon can replace any single contiguous string of ones or more in 16-bit segment hexstat consisting of all zeros. So double colon can only be used once within an address, otherwise the address will be ambiguous, known as a compressed format. So for example, here we had colon 000. What we can do is we can compress these 3 hexstat as a double colon. Like this, again compress it even further. 2001 db8 9f0 a00 colon colon 1. If you look at before one, it was 0 0 colon 0 colon 0 colon 0. These 3 we can represent it with a double colon. Now it's important to know that this double colon can be used only once. You can't use it more than once, because then it will be, the IPv6 will be ambiguous. So for example, this is, I don't know, it was in the one of the questions, in the interview questions, I think it was 2001. Well, like this, if we have address like this, say 0A00 and then 0000, like this, there's got to be 8. So 1 2 3 4 5 6 7 and 8, right? Now it's important that these zeros, you can either compress these ones, contiguous zeros with a double colon, or these zeros with double colon. You can't do both. So it's error if you do like this: 2001 double colon A00 double colon 1. That's not correct. So you either got to put the zeros on this side, like this, or on the right. It can't be used. The double colon cannot be used twice. The IPv6 prefix length, IPv6 does not use the dotted decimal subnet mask like we had in IPv4 to identify which portion is a network and which portion is a host address, but it uses prefix length. Indicates the network portion of an IPv6 address used in the following format. So IPv6 address, and then we have the / and then prefix length. Prefix length can range from 0 to 128. Typical length can be /64. For example, /64, this is the address 2001 0db8 000:111 /64. What this is saying, okay, the first 64 bits, which is going to be these ones here, are the network address, and the last 64 are interface ID address. 64-bit, because one bit here, this number 2 is 4-bit. So 4 and 4 is 8, and 4 12, and 4 16. So this hextet is 16. Plus 16 is 32, plus 16 is 48, plus 16 is 64. So these are the 64 bits for the prefix that we're using. And the rest 64 bits are for the network ID. The types of IPv6 address, just remember the IPv6 address does not use a broadcast anymore. It does have a unicast, like IPv4, one-to-one communication. It does have a multicast, one-to-a-group, like an IPv4, and it has a new type of communication, anycast. An IPv6 unicast address is any IPv6 unicast address that can be assigned to multiple devices. A packet sent to an unicast address is routed to the nearest device having that address. So 1 to the nearest. So say, imagine the two servers, they have the same IP address. The client, when it's close to one server, it will actually access that server that's nearest to the client. Unlike IPv4, IPv6 does not have a broadcast address. However, there is an IPv6 all-node multicast address that essentially gives the same result. So we have an all-node multicast address. An IPv6 unicast address, there are 6 types of unicast addresses. First is a global unicast address. A global unicast address is similar to public IPv4 address. These are global unique, internet routable addresses. Global unicast addresses can be configured statically, or we can assign them dynamically. The second type of addresses are called link local address. Link local addresses are used to communicate with other devices on the same local link. With IPv6, the term link refers to a subnet. Link local addresses are confined to a single link. Their uniqueness must only be confirmed on that link because they are not routable beyond the link. So what we're talking is within the local area. So they don't go to another part of the network. So as long as they are unique within that link, it's okay. So for example, a router can have 3 same link local addresses on 3 different interfaces, because from one interface the link local address is not going to go to another interface. So that's allowed. For example, let's say this router, take one router, say it's got interface FA00, it's got interface FA01, and it's got interface FA02, for example. This can have IPv6 address, global unicast, yeah, so something like that. 2001 DB8 ACAD /1/64, right? That's one global unicast address, as well as FE80:1. That's link local address. Now this FE80:1, we can add it to all our interfaces. For example, that's for router 1, because this link local address will never go to and clash with this link local address because it's on the link, on that link only. It will never go to another network. These are networks, so every interface on the router is a different network. Yeah? Then we have a loopback addresses. The loopback addresses is used by host to send packets to itself and cannot be assigned to physical address. Similar to an IPv4 loopback address, you can ping an IPv6 loopback address to test the configuration of TCP on the local host. So have you installed your network card correctly? All the TCP IP stack is working correctly? Okay, fine. ping the local loopback address, and if you get a reply, everything is working. So we can represent it as a : 1. So when you think of it as a, this is loopback address, right? Loopback address for IPv4 was 127.0.0.1. Well, anything in 127 is a loopback address. Then we have an unspecified address. An unspecified address, just : it cannot be assigned to an interface, and it's only used as a source address on an IPv6 packet. An unspecified address is used as a source address when the device does not yet have a permanent IPv6 address, or when the source of the packet is irrelevant to the destination. So if the device doesn't have an IPv6 address, it can use unspecified address for a routed solicitation and messages like that. Then we have a unique local address. IPv6 unique local addresses have some similarities to 1918 RFC 1918 private addresses on IPv4, but there are significant differences as well. Unique local addresses are used for local addressing within a site or between a limited number of sites. These addresses should not be routable in the global IPv6 address. Unique local addresses are in the range of FC00:/7 to FDFF:/7. It's like a private addresses, yeah? Okay, we don't need the private addresses in IPv6 because we have so many, but you can use them if you want. They are not routable on the internet. And then last one, we have a IPv4 embedded addresses. The last type of unicast addresses type is the IPv4 embedded addresses. These addresses are used to help transition from IPv4 to IPv6. IPv4 embedded addresses are beyond the scope of this course, so we're not going to learn about anymore in embedded addresses. Then we have a IPv6 linked local unicast addresses. In the IPv6 linked local addresses enables the device to communicate with other IPv6 enabled devices on the same link and only on that link or subnet. Packets with a source or destination linked local address cannot be routed beyond the link from where the packet originated. So it cannot be routed. The one thing I can remember, this is maybe IPv addresses 169.254. They're not routable. They are just within the link, so the devices can communicate with each other. Every IPv6 enabled network interface is required to have a linked local address. Enables the device to communicate with the other IPv6 enabled devices on the same link and only on that link or subnet. The range is FE80:10 up to first 10 bits are like we see in the binary 1111, 1110, and then 10, up to FEBF. Structure of an IPv6 global unicast address. IPv6 global unicast address are global unique and routable on the IPv6 internet. So they are global addresses and are routable, equivalent to public IPv4 addresses. I can allocate IPv6 addresses blocks to the 5 RIRs. Currently, only global unicast address with the first 3 bits 001 or 2000:/3 are being assigned. A global unicast address has 3 parts. First, you have a global routing prefix, subnet ID, and interface ID. So, for example, if your company has went to buy an IPv6 address, public IPv6 address, then it's going to get 48 bits that will be assigned. Then you have a 16 bits that you can create different kind of subnets with it. That will give you like 65,000 different, just around 65,000 different subnets that you can create. And then we'll have a 64 bits available for our interface ID. Okay, now we'll do a demonstration on assigning IPv6 address. So I'm going to open that PC again, PCA. You've seen me assigning IPv4 address. Well, it's very similar here for IPv6 addresses. So click. Maybe just. Okay. Right, we were here. Okay, let me close this first and start again. So click Start, Control Panel. network and internet, network and sharing center, and then local area connection here, properties. Now we don't select IPv4, we select IPv6. IPv6, we go to properties. Again, from the previous test or labs or chapters, there's already configuration here, but it would be like this usually. And then if you want to configure it statically, we say use the following IP address and give an IP address. So for example, global IP address 2001 db8 colon I don't know what we said, a colon ACAD colon A, right? And then we have a prefix length 64, and then the gateway. The gateway, you can give an IP address like a global IPv6 address, or you can create the link local of your gateway. So for example, FE80 colon 1, that's your router's link local address. Okay, and to verify it, we will open command prompt. So CMD, and we type ipconfig, so let's say all. Okay, here we can see we have IPv4 address. No, we don't. Okay, so because we have selected the DHCP, so DHCP enabled, yes. DHCP enabled, yes. Auto configuration enabled, yes. So you can see it didn't talk to DHCP, it just assigned itself a PIPA address, automatic private IP addressing. Something 169.254.something.something. So pick 333.154. And we can see we have a default gateway here, FE80 colon 1 that we assigned. That's percentage time 15. Just says it's for the network card to identify the network card. It has assigned itself a link local address, right? And the address that we did assign. So 2001 db8 ACAD colon A, that was the address that we assigned. But it will assign a link local address for itself as well. Okay. Dynamic configuration of global unicast address using SLAAC. So that stands for Stateless Address Auto Configuration, which is a method that allows the device to obtain its prefix, prefix length, and default gateway address information from an IPv6 router without the use of DHCP version 6 server. So a client machine will go and assign itself a global unicast IPv6 address without the help of DHCP server. Using SLAAC, so SLAAC, devices rely on the local router's ICMP-v6 router advertisement messages to obtain the necessary information. IPv6 routers will periodically send out the ICMP-v6 router advertisement. By default, Cisco router sends an RA message every 200 seconds to the IPv6 all-node multicast group addresses. An IPv6 device on the network does not have to wait for this period. They will send for the router advertisement. They can send something called router solicitation message, right? So router solicitation says, okay, well, I need an IPv6 address. Please, can you send me that address? Now, if I open the notepad again, imagine we have the router. So this is R1, and R1 address is 2001 db8 ACAD I don't know, 8888, and then something else, 00, let's put all zeros, 000, 000, 000, 000, 1. Okay, I can compress this, right? So I'm going to write it in the compressed format, so colon 1, like that. Now we have a PC who just came online. Now the PC is going to send something like a router solicitation message that is going to want the router's network or prefix ID or prefix length. Now if this is /64, what we're saying is this is our network, right? And that's what the PC is looking for, because the host or the network ID is going to build it itself. So if we look at the PC, for example, the PC, let's use a MAC address of the PC. So PC, let's go to the PC, open that we had there. I don't know if I can copy. This is my MAC address of this PC. My PC here? Yes. Okay. Now, the PC is going to use this MAC address here that we have as for the network ID side of it. Right? When you look at this MAC address, this MAC address is 48 bits. So this equals to 48 bits. But we do need 64 bits for our network ID. Sorry, for our interface ID. So what the PC is going to do is going to take the MAC address like as is, right? It's going to add it there. Let's get rid of these and put a like this colons. Get rid of the dashes. It's like this. Yep, that's the MAC address without the colon, but without the dashes, but with the colon. So 000C. What the PC is going to do is going to actually divide this MAC address into halves, right? And in the middle, is going to add FF, FE. Now, as you can see, now this PC has got the interface ID ready. That's a 64-bit. It's got the back from the MAC address. Is build his 64-bit interface ID. Now this PC is got two parts, yeah. So when you think like this, here we need a prefix, right? And then the last one is the network ID. So here is network ID. The network ID is already has. Boom. If I could copy this, I will paste it here, but it won't work that well. Now it needs a prefix ID. So for the prefix ID for this part here, it's gonna do a router solicitation. It's gonna send a message to the router, say, okay, I need this part, and the router will reply with the router advertisement, say, okay, here's your part of the IPv6 address. Now it's got this as a network ID. So I'm gonna copy this. Done. Now it needs this, the prefix. Router will tell it that will be here. So let me go to the front, put it there. As you can see, now this PC has got a unique IPv6 address without the help of the router. What is done is used his MAC address and is used a prefix length from a prefix address from the router with the router advertisement, and it's got a unique IPv6 a global address, and it can go and access the internet or anything they want without the help of the DHCP. We didn't use the DHCP. So IPv6 Unicast routing command enables IPv6 routing. So first you have to enable IPv6 routing. Router advertisement messages can contain one of the following three options. So first we can use a slack only, which says only use what the router is telling you. So it gives you the prefix length, the gateway, and how long you can use that. Or it says you can use me slack and go and ask the DHCP server for extra information, like for DNS, for example, the domain name. So there's some other information where the router advertisement is not going to give you, where the DHCP will give you. Or the last option is says, okay, ignore me, don't get anything from me, just go and ask the DHCP server for the IPv6 address. EUI64, IEEE defined extended unique identifier, EUI, or modified EUI-64 process. This is the process I was telling you about. Using the client's 48-bit MAC address and instead insert a 16-bit in the middle of 48-bit MAC address to create a 64-bit interface ID and use a flip URL bit 7. So for example, we are taking the MAC address and we're splitting that MAC address, and we are inserting FFFE in the middle. So like we had here, we inserted FFFE in the middle. Now the 7th bit, which is here, it's going to be here, it's going to be flipped. So if you convert this first 0, all right, convert that, so 1, 2, 3, 4, so that's the first 0 here, that's that 0, then 5, 6, 7, 8, that's the second 0 here, Now the 7th bit, which is 6, 7, this one will be flipped. If it's 0, will become 1. If it's 1, will become 0. So actually, this one will be 0.2.0c will become. Organization unique identifier is the OUI is 24-bit 6 hexadecimal digit vendor's code assigned by IEEE. And then device identifier, this is the last 24-bit on the MAC address. So if you look at again, if we open the MAC address, this was our MAC address here, right? Or the PC, or the virtual PC. So these 24 bits here are the organizational unique identifier, and these 24 bits here are interface identifier. These ones, if you're producing a network cards, you will go and have to purchase these. These are 24 bits. You can't change them; they are given to you, and then you will assign interfaces, your interfaces, these last 24 bits. So it's called organizational unique identifier, the first 24 bits, because that's 4 bits. That's another 4, 8, another 4, 12, another 4, 16, another 4, 20, another 4, 24. So that's 24. 1 is representing 4 bits, yeah? Okay. Assigned IPv6 multicast addresses. The multicast addresses on IPv6 is similar to IPv4 multicast addresses. There's 1 to a group. IPv6 multicast addresses have a prefix FF00::8. Always start with FF. As soon as you see FF, that's a multicast address. Multicast addresses can only be destination. You can never have as a source. A group cannot send a message. A single device can send a multicast message, but not a group. There are 2 types of IPv6 multicast addresses. We have assigned multicast and solicited node multicast. Assigned multicast addresses, there are 2 common in IPv6 multicast group. They have FF02::1. This means it's all nodes multicast group. This is a multicast group that all IPv6 enabled devices join. A packet sent to this group is received and processed by all IPv6 interfaces on the link or the network. This should remind you something. This has exactly the same effect as a broadcast in IPv4. You have a multicast group FF02::1 that all PCs, every device, every network device is joining. So as soon as you send the message to this group, everybody gets it. Then we have FF02::2. This is all router multicast group. So all routers will join to this group. This is a multicast group that all IPv6 routers join. A router will become a member of this group when it's enabled, and an IPv6 router as an IPv6 router with an IPv6 unicast routing global configuration command. So as soon as you say IPv6 unicast routing on the router, that's a global configuration command, the router will join this group and this group. And then we have a solicited node multicast addresses. It's an addresses that matches only the last 24 bits of the IPv6 global unicast address of the device. They start with FF02::0:0:0:0:1:FF00::104. Prefix with the far right 24 bits of its unicast address. This is for communication like a multicast communication with a local group rather than with everybody on the network. On this demonstration, I will show you how to configure IPv6 addresses on the network devices. So I have a GNS again. I'm going to start this router. So click Start and open Secure CRT. Once this router boots, we can assign IPv6 address. Okay. I'm going to pause to see what's happening. Oh, here we go. Oh, there's already configuration from previous lab. Class, yeah. Show IPv6 interface brief. Yeah, it's got an IPv6 address. You can see it's got, I have assigned it. Link local address, they're exactly the same. Both interfaces, they have the same one. So for example, for router 1, I'll put 1 FE80::1. For router 2, FE80::2, and so on, to identify them correctly. But you have to go to global configuration command and then say enable IPv6 unicast routing, IPv6 unicast -routing. After it's enabled, then you go to the individual interface and assign IPv6 address. So IPv6 address 2001 DB8. Let's change it. ACAD::1/64. That's our new address now. And then we have a link local address. So IPv6 address FE80::2 this time. Say link local. This is link local address. And show IPv6 interface brief. Okay, next we're gonna see the show IPv6 interface E00. Sorry, FA00. And as you can see, this router has joined onto two groups. Well, 4 groups here we can see. But the first group that we talked about is all nodes, and then the routers group as well. Okay, thank you very much. This has been Astrid Krasniqi. Thank you for watching my video, and I'll see you in the section 8.3 connectivity verifications.